your tutor for today, chemistry, and we'll be handling the mathematics course. So please, if you can hear me, I want to see a few reactions, maybe signify with an emoji or something. So I'm sure that I'm audible and then I can kickstart. Can anyone hear me?
Yeah, I can hear you. I can hear you.
All right, fine, wonderful. So I'll go ahead. All right, so quickly as an aside, before we go into what we have actually for this week. So last week we had a little technical issue with the network and then some screen sharing issues. So I promised those who are on the call that we're going to wrap up with the rest of the slides for week 1 and then now go over what we have for week 2. So in order to fulfill that promise, I'll just look through a few important slides that we omitted from the last week's class so as to make sure that everyone's carried along. And then we'll move over to what we have for this week, which is week 2. So last week we were talking about number sets, set theory, and all of the related terminologies. So I just want to use the diagram here to point out a few examples, show some themes that are necessary to be understood in set theory. Then we move over to what we have for week 2. Right. So in talking about set theory, of course, Venn diagrams are useful because these are the visual illustrations for understanding what it means to combine sets and all the set operations that are going to be necessary for solving word problems. So this is a Venn diagram, right? These are Venn diagrams, plethora of examples. So they illustrate the relationship between the sets. And so I'll just go through each of what we have in this diagram. I think it's really important, especially for understanding set theory. This is like the crux of the matter. And then look at 1 or 2 problems and I'll move over to it as quickly as possible. Hopefully we have enough time to cover all of that. So the first diagram we have here, top left, we have 2 sets. Set A illustrated by the circle on the left and set B illustrated by the circle on the right. Now, usually the sets are bounded in a Venn diagram. The sets are bounded by a rectangle, which is used to denote the universal set, right? And now, so anything that is in the universal set that is not in A or B would be placed outside this rectangle, right? Outside, but not in any of the circles. So the first operation we have here is A union B, right? Now, what A union B simply means is, and of course you can tell that from the shaded area, what A union B means is everything that is in A combined with everything that is in B. And of course, as you can see, everywhere in A is shaded as well as everywhere in B. So it is a union of A and B, right? So it's a combination of the 2 sets. So add every element you have in A and every element you have in B. And so the shaded area illustrates what this operation stands for. Now, if we go to the next one, which is A intersection B, you can see that only this middle place is shaded. What does this mean? It means that this is the place where you have a meeting, you have an intersection, as the name implies. So what element in A can you also find in B? That's what it means to have an intersection of the sets. So you have set A and you have set B, and there is an intersection. There are elements that are in both of them, and this is what this area signifies. Of course, where the 2 circles overlap, and so that's why we have the shaded area as green, right? So there might be cases where there is no intersection, right? And so there's no element in A that matches any elements in B. And so you just have these 2 circles, one here drawn, and then there will be a space. There will be no overlap of the circles, and then this other one here drawn, and then there's no overlap. So you have no intersection. There are sets like that. There are cases like that. But here you are illustrating that there is actually an intersection. Fantastic. Now the next operation is A union B minus A intersection B. Right? It's denoted by this triangular symbol, right? And so if you do the math, when we get to examples to become more clearly, this is illustrated by every other place that is not the intersection. So it is the what do we call it now? The prime of the intersection set. So you can see in the intersection set only the middle is shaded. For this operation, everywhere is shaded except the middle. Then the next one we also have is A prime, right? So A prime simply means everywhere else but not A. And so you can see that everywhere else in this set is shaded except the circle that is A. That's what A prime means. Now, A intersection B prime means, so first of all, we have two operations here. We have the prime and then we have the intersection. Now, B prime is what? Everywhere that is not B, right? Everywhere in this rectangular set that is and set of A and B that is not B, right? So pretty much everywhere here, and then the circle of A. Now, they now say intersect that with A. And then what do we say intersection is? Intersection is the meeting point of two. So if I'm intersecting the whole of A with everywhere else that is not B, you can see that the common place, the meeting place is this area, right? Because first of all, this is B prime, and then, sorry, the whole of this is B prime, and then I'm intersecting with A just here. And so they meet in this shaded area that is A. And then the same thing applies here. This is just an irrational, that's A prime intersection B, where everywhere else that is not A prime is A, that is not A is A prime, and then you're intersecting that with B. Now, if you intersect the whole of this rectangle and the circle of B with B itself, you can see that the meeting points that you have is here, of course. Then the next operation we have is A union B prime. And so in A union B prime, we are saying B prime is excluded. B is excluded. That's what B prime is, right? Everywhere else that is not B, and then you are adding it to A. Now, everywhere else that is not B is the whole of this rectangle and the whole of circle A, and then you're adding it to A already, which A already is inclusive. So pretty much you are going to shade every single place that does not have B in it, right? And of course, this place is shaded because this place is also part of A. Wonderful. And then we go into the next operation. Now, this operation is pretty special when it comes to set theory because this is a law referred to as De Morgan's law, that the intersection of A and B prime, so A intersection B prime is equal to A prime union B prime, and the representation, the physical representation of that is everywhere else is shaded except the intersection of B. And of course, it's obvious from this. So if I say A intersection B, normally the operation inside this bracket, A intersection B, is just here, right? But then now I put a prime on the outside, and prime is everywhere else except what's here. So everywhere else is everywhere outside this particular spot, and that's why here is not shaded and everywhere else is shaded, right? Now, the last one and the final one is A union B, then prime. So A union B is, as you can see from the first example, this is A union B. But now, by saying A union B and then putting a prime on the outside, I now want to represent everywhere that is not A union B, but is still part of the universal set. And so you see that this is an opposite of this, where now here is not shaded, which is A union B, and then everywhere else that is not A union B is shaded. So this is just to give you like a physical guide, a representation to how sec actually work in real life. And so when you are able to do them, when you're able to understand and picture them graphically, you can now see how it plays out when you solve examples. And so we'll just do one or two examples quickly before we move on. So the first problem we have here is this. So U connotes the universal set, which is, as I stated in the diagram, the rectangle, right? The universal set contains all the other smaller sets inside. So A and B are subsets of the universal set, and C, of course, in this case. So U is A, B, C, D, E, F. So this is the set. These are the elements in the universal set. And so they tell us that A is ABC, B is C, D, E, F, C is C, D, E. So we are now asked to find this, right? So A intersection B, union A intersection C. And of course, to tackle this quite simple is you handle the one in the first bracket, handle the one in the second bracket, and then find the union of the two answers. So the first thing is to do A intersection B. Now, A intersection B simply means what are the common elements that you have in A and you also have them in B. Now, looking at the members of the elements A, B, C for A and C, D, E, F for A, we see that the elements that match that are in A and also in B is just C, right? So the set A intersection B is going to contain only one element, and that's C. Now, the next one is to do A intersection C. So again, what are the matching elements in A and C? As you can see, C is C, D, E. So the matching elements A and C is also only C. So we have the A intersection B and we have A intersection C. And so combining them means adding up all the elements in these two sets, and of course C is the only thing we have. And so the final answer is just a set containing C. Now another example is this. Now so we are using numbers here. So we have the universal set, we have the set of A and the set of B, and then we are asked to find A minus B prime. Now, what does A minus B mean? A minus B means what elements do you have in A, but then are not in B. So basically, you're taking the whole of set of A, right? Removing the elements that you have in B from that set of A, and then what you have left is a set of A minus B, right? So, and then of course, we are now asked to find the prime of that. So first of all, we have A has 3, 5, 7, 9, 11. B has 7, 8, 9, 10, 11. So if you are doing a subtraction of that, we can see that B has 7, 8, 9, 10, 11. A has 3, 5, 7, 9, 11. Now we see 7, 9, 11 are in B, and they're also in A. So we have to subtract it. So basically, we are taking out these 3 because they are in B. So it's a subtraction, it's a removal. And then we are left with just 3 and 5. So the set of A minus B is now set that contains only 3 and 5 as elements. But then the question actually asks us to now find the set of A minus B prime. And so, like I said, the prime is going to be everywhere else that is not this. And of course, the only way you can do that is by subtracting it from your universal set, right? So universal set is 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And then you have the elements A minus B as 3 and 5. So A minus B prime now is to take out these 2 elements from our universal set. And of course, in doing so, you are left with every other thing that is not 3 and 5. So our set of A minus B prime will give us as our final answer. And so this is just like a brief overview of what set theory entails. So it's important to understand the terminologies, how they work, what to do when you're presented with any set theories, and then understanding this is going to be very useful. This is like the building block foundation, and then every other thing you're going to see is going to pretty much revolve around these terminologies: union, intersections, complement. So okay, so yeah, just to point that out, another word terminology that you normally see is complement, a complement or a prime. So both of them mean the same thing, and then difference as well. So I think these slides were made available to those concerned last week. And so if there are any questions concerning this and the subsequent thing we're going to be doing soon, feel free to raise them up at the end of the class. So I think that takes care of that, and then we can move on to what we actually have for week 2, which is sequences, series, and binary operations.